Hello everybody. It's time for the project. The project will involve image segmentation and object localization. Image segmentation means breaking the image into multiple parts and assigning to every pixel some type of indicator for which object it is part of. And object localization is taking groups or clusters of those segmented pixels and deciding where is the center of your object. So the primary project most people are going to work on is tracking juggling ball positions, hopefully in the webcam video. And if you have a Mac, then either we can try and get it to work, or more likely you're going to do it for still images. There are multiple levels of difficulty here. So probably the easiest, which you might even be able to do in one day, is can you track the position of a single ball if you know what its color is in advance. It's a little bit harder if you are not told what its color is in advance. It's even harder if there are more than one ball and you know what, and they're all different colors. It's even harder if there's more than one ball, but they're all the same color. And it's even harder if you don't know how many balls there are going to be in advance and you don't know what their colors are. Potentially the same, potentially different. So the techniques that you're going to use to do this have a lot of real world applications. And the last level is quite tricky. So I think it'll be a sufficient challenge for anybody. If you are a particularly advanced programmer and you want to try a different task where you will put bounding boxes around set cards and then automatically determine what properties each card has, you can talk to me, but you do need special permission to work on this project. Okay, so let's talk about segmentation and localization. I got this from, I think, a college level student project where they were trying to automatically locate grapes in an image as, for example, part of a robot picker. So segmentation refers to masking all the pixels you don't care about. Masking just means turning them a background color. And then adding colors to pixels you do care about that will let you see them as belonging to distinct objects. So you can see here this kind of the kind of grape colored pixels are grapes. And then the blue is the background, and then yellow seems to be potentially leaves or maybe bright leaves. It's hard to tell. So that's segmentation, and localization is just being able to say where is something on the screen. So put a dot in the middle of a cluster of pixels that all represent the same object. So you have been building up a lot of tools that are potentially relevant to this task. So you've got all these filters. You've got brightness, thresholding, and color masking, and blurring, and sharpening, and lightening and darkening, and all the various convolution filters that you've been doing. And then we have k-means clustering, which we used to try and cluster colors. But you can use clustering also to cluster pixels that are close to each other geometrically in your original image. And I'll show you what that looks like in a minute. So before we do that, I wanted to show you the slides from this college level project, the grape detection project. And I want you to notice what kinds of things they're doing. So here they're saying the input is a Vine's image with some grapes, and the output is a Boolean matrix of the image's size with a 1 if the matching pixel is on the image of a grape and 0 if it's not. So in other words, imagine each pixel is Boolean, and a pixel that's on top of a grape, you'll put a 1, and a pixel that's not on top of a grape, you'll put a 0. So that's segmentation. You're segmenting the image into meaningful and unmeaningful parts. So what they're going to do is they're going to process their image in a series of steps, and this is usually called a pipeline. So they start by reducing the image's color numbers, and what they mean is the same sort of thing that you did before. Like, let's take an image with thousands of colors and make it only have 6 colors. And then they try and eliminate non-grapes by applying a series of masks. And you haven't heard of the names of these masks before, but they're similar to color threshold mask or other types of mask. And then they apply several other masks for other purposes afterwards, and then at the end they have their grapes. So the main thing I want you to take away here is this idea that you're processing the image in multiple steps where the output from one filter becomes the input for the next filter. So I don't expect you to understand kind of the details of what's happening here, but I just want to illustrate what that would look like at a college level. So here they've used a color reduction filter, similar to what you guys did with k-means clustering. Here, they say we'll derive the clustering output. I assume they mean they took the derivative. And it's not really important kind of what that means or why, but it's taken this colored image and it's only kind of highlighted pixels where there was a big change between colors. So you can think about it as kind of bringing out edges. And what we're noticing is a lot of these edges have a sort of roughly circular pattern. And so they want to be trying to bring that out. And so what they did next is they took this image, they found some edges, and now they're running a filter where they're going to try and calculate the density of the edges. So you might have an area and kind of count how many pixels in a little area seem like they're edge pixels versus not edge pixels. And that would be a measure of the density of edges. And maybe the thing that they care about involves a particular density of edges. So where there's leaves, there's a high density of edges. Where there's background, there's a low density of edges. Where there's grapes, there's kind of a medium density of edges. So you could do a filter based on how dense are the edges in the output from your last filter. And then they have a whole series of other masks, and I can give you the slides for these if you want to kind of look at them. But what I hope I'm bringing out here is the thing that I said. In order to be able to get the effect you want at the end, you need a pipeline where the output of a filter becomes the input for the next filter, and each filter is designed to highlight a particular thing or simplify a particular thing in the image or calculate a particular thing that's going to be useful as a step towards your final goal. So, two big concepts that I want to highlight here. One is this idea of the pipeline that I said. So in our project, you might do a k-means cluster based on colors, but then you'll take the output of your recolorized image and then run an outline filter on it, a convolution filter with an outline kernel, and you'll take the output of that and then you'll threshold it. So that would be an example of a pipeline using filters that we have made. A particularly nice way of organizing this code would be something like this. You could make a class called pipeline that implements pixel filter. And you'll notice down here it's got the process image method. But what we're going to do is we're going to make a list of other pixel filters. And these are the filters that we want to run in sequence. This is the pipeline. So in the constructor, we'll create all of the filters. So I'm going to create convolution filter 1 and convolution filter, another convolution filter. You're not allowed to change the constructors of the pixel filters. So if you want to be able to set particular parameters, such as which kernel are they going to use, you'll need a setter method. So for my convolution class, I added this set kernel method where I can tell it which kernel it's going to be using. And then you add your filters to this filters list. Then in process image, I just have a loop where I loop through each filter one at a time. I give my filter the input image and tell it to process it. But then instead of displaying the processed image, I'm going to replace the image variable with the output from that filter. So in other words, each time I run my process image method, it's going to update my image with the output from that filter. And so then when it does the next loop, that's going to become the input to the next filter in my list. So this is what implements the pipeline. And then at the very end, when we say return image, you get to see displayed what the output is from that entire sequence of filters. Big concept number 2 is what I call blob finding. Blob finding means sort of what it sounds like. If you have a whole bunch of white pixels or a whole bunch of similarly colored pixels that are all kind of next to each other in your image, how can we have the computer understand that those are all members of the same object? How can we understand that they're all clustered together? So you've already done clustering like this. We're going to turn every pixel in an image into a point in red, green, blue space. And then you're going to find clusters in red, green, blue space, which is a way of saying which colors are close to which other colors. And then you reassign colors based on that. So this is clustering by similarity in color. Blob finding is clustering by proximity in the original image. So usually the first step is to work in black and white. So you're going to threshold your image so all the pixels are either pure black at 0 or pure white at 255. We're going to ignore the black pixels because those are going to be background, and we're going to turn each white pixel into a point object, similar to last time. Then you're going to cluster not to see which points are close to each other in 3D color space. You're going to see which points are close to each other in the two-dimensional space of like the row and column from where they came from in the image. And then you might reassign random colors based on that. And the only reason to assign random colors is so that you can kind of visually see the computer thinks like this is one object and this is another. So I think a picture would go a long way here. So I think these are mitochondria maybe. I don't know what these are. Anyway, whatever these are, like you and I as humans can see they're a bunch of kind of long Cheeto shapes. This has been thresholded already, and even though it's not pure black, pure white, you can see that the background pixels are all black. This is the result of applying a clustering algorithm, but based on proximity. So you can see like all of these white pixels that were close to each other have all become green. And these ones here have also become the same green because the clustering algorithm believed that these are all part of the same object, which you and I as humans can tell was probably a mistake, but is not too far off. Whereas this little Cheeto right here has become its own color. So the clustering algorithm assigned all of these pixels as part of the same cluster. All right, so due at the end of the day. If you want permission to work on the card recognition task, email me and I'll tell you if that's okay. But please do tell me why you would prefer to do that one. Otherwise, and I'm expecting the majority of students to work on the ball tracking one. Try the following baseline algorithm. Find a uniformly colored object that you happen to have lying around. I'll pass out juggling balls next time when I return. But I want you to apply a color mask, which you've already programmed from before, where you try and turn pixels for your uniformly colored object white and everything else black. Then I want you to just loop over that image and find the average x and y coordinate of all the white pixels. And then I have another video which shows you how to use the drawable interface, which will let you draw things on top of the image. And I'd like you to draw a small circle right at those average XY coordinates. And if you do it right, this actually should be probably level 1. This should do like a tolerably good job of tracking the center of a single ball. And we'll talk more next time about how you could kind of level up to these more advanced levels. So go ahead and check out the Schoology project. Good luck, everybody.